Okay, great. Our second talk for this afternoon is by Marsh Boedihardjo. I'm sorry about that. From Irvine, who'll be talking to us about sharp matrix concentration.
Okay, so yeah, I feel so lucky to be here because yesterday after I booked the taxi didn't come. I ended up walking to the airport for 3 miles, and yeah, just took the flight just in time. So feel so lucky to be here today. Yeah, I have to carry my luggage to my airport for 3 miles by walking. Okay. All right, so yeah, today I'm going to talk about some sharp versions of matrix concentration inequalities. Okay, so some motivation. Start with this very general problem. Suppose we're given a random matrix X, how large in general is the X vector spectral norm? So there's some well-known result about this. There's a very classical result, matrix kinship inequality. So if X is a matrix where all the entries are jointly Gaussian and centered, in that case, there is a pretty sharp estimate up to a factor of square log D. So it's bounded below by square roots of the norm of EX square, bounded above by the square log D of times the square root EX square. So the square log D factor is sharp. And then the small general one, if you can write the random matrix, is a sum of independent random matrices. They don't have to be IID, just independent and centered. There's also a sharp estimate. By sharp, I mean just sharp up to a factor of log D, because if we replace the left-hand side by E of norm X square and the square root, the left-hand side would be at least the right-hand side if you remove all the logarithms. So these two are both of them pretty sharp up to a log factor. Now, today's talk is a bit off topic, but pretty much related. I know they should be useful in this learning theory. The remaining question in the literature is to remove these log factor. So that's the hard part, how to remove the log factor. That's the head question remaining unsolved. Okay, so first of all, why is the log factor necessary in the general case? Well, it's not needed actually in many cases. For instance, if it is like GUE or GOE, all the entries are IID, standard normal. In that case, we don't need the log factor because EX squared is identity and norm of X is approximately 2. So in that case, the log factor is not needed. But there's also a case, this is a very special case of diagonal matrix. In that case, the log factor is needed because if you take the norm of X, it's just the largest value of the diagonal in absolute value. And from that one, there is a square log D factor. So in this very special case, the log factor is needed. In that case, it's not needed. So these two are the two extremes, okay? All right, so, but actually in most cases, it's not needed. So what's the big difference between these two, okay? Both are Gaussian matrices. Well, the first one is very non-commutative in the sense that if we take another copy of X, let's call that Y, let's say Y is an independent copy of X, X and Y are not commuting almost surely in the first case. In the second case, if we take an independent copy of X, call that Y, X and Y always commute. So from that point of view, the first one is very non-commuting. And the second one is commuting. So this suggests that if there is enough non-commutativity, then the log factor could be removed. Okay, so from this point of view. Okay. All right. Now, of course, because everything here is quantitative when it comes to estimation of the spectral norm of the matrix. So how do we quantify non-commutativity? Okay, so Trop made the attempt to quantify non-commutativity. He introduced this quantity. So if we are given a Gaussian matrix X with, matrix with jointly Gaussian entries, not necessarily IID, just jointly Gaussian. So if we take an independence copy of X, then we take XY, XY, and then insert the unitaries in between, take the expectation and take the norm, take supremum over all the unitary. Okay, this is some kind of, some way to quantify non-commutativity. So that's what Trop proposed. And he did prove something. We can improve the square log D factor, reduce the square log D factor to log D to the power 1/4. Yes.
How this corresponds to non-commutativity? I mean, what would happen here?
Okay, so first of all, this one is always less than or equal to this. But if they commute, if X and Y commute, then this will be equal to this. So if this one is much smaller than this, then it means they're very non-commutative. Okay, so let's say so first of all, this second order term is always less than or equal to this term. If you don't look at the log factor, this Wx is always less than this. But in the case when they commute, these two will be the same. So if they commute, then there is a square log D factor here. But if they don't commute, then this will be much smaller than this, and this you can neglect this term if they're very non-commutative.
Is there a way to see from that expression how Wx?
So, well, actually, the way to estimate non-commutativity is Wx divided by this. If it is equal to 1, then they commute. If it is much less than 1, then that means they're very non-commuting. Kind of like that. So that's the way to quantify non-commutativity. So, for example, if X and Y commute, then take all these unitaries to the identity. You have xy, then becomes ex squared times ey squared, the norm of that. And that's like the norm of ex squared. And then you will get Wx equal to this if X and Y commute. Okay. All right. So yeah, the idea is just to reduce the square log D to this one, but with the cost of adding a second order term that measures non-commutativity. And this second order term is going to be small if it is very non-commuting. This one will be much less than this if it is very non-commutative. Okay, so that's what Trop proved. Okay, so of course the two obvious things not very good. First, the square log D factor is not completely removed. It's only reduced to log D to power 1/4. Second thing is this one is very hard to compute in general. Even for very simple cases like GUE or GOE, it takes maybe half a page to compute. For general matrices, it might not even be possible to compute Wx. Okay. Anyway, so Trop made the first attempt in this direction. I just try to remove the square log D in the first factor and then add a second order term that measures non-commutativity. Okay. All right, so we're going to use another approach. Yes.
What's wrong with just using? What's wrong with just using the standard, commutator, right? That's how you usually
In this context, it doesn't work. You know, x, y minus y, x type of thing.
No commutator. No commutator is not a good estimate because okay, it's the other way around. We want a quantity that is big if they commute and small if they don't commute. Commutator is the other way. Commutator is big if they don't commute and small if they commute. It's the other way.
I guess maybe another way to ask is, can you relate the commutator to Wx? I mean, if the commutator is small, can you say the Wx will be large and vice versa? So we're just trying to get a sense of, I mean, I think some of us maybe are not familiar with this measure of Wx. We're trying to get an intuitive sense for it.
Is there a marker? Oh, on the board, okay. Okay, so let's see. Yeah, so first of all, always Wx is less than equal to ex squared to the power this. Okay. Second, if x and y commute, then Wx is equal to this. The reason is just very short proof, because Wx will be at least norm of xy to the power 1/4. Okay, and then this will be equal to, because they commute, so, and they're independent, so you have ex squared, ey squared, norm to the power 1/4. Okay, they're the same. Y is just an independent copy of x. So this is just this thing square. Because this is less than with this, and if they commute, then this is the greater than with this. Okay, so what does that mean by contrapositive? If this is much less than this, then they're very non-commuting. And so if Wx is much less than this one, they're very non-commuting. If it's very non-commuting, then maybe the square log d factor can be removed. So this is much less than this, so this would disappear. And then at least we can reduce the square log d to this one. That's what short proof. If they're very non-commuting, then we can remove the log d factor. Yes.
So let me ask a slightly different question, which is really, so what prevents me from having Q1 to Q15 and then just writing a long sequence of xy's 16 times, and then have a power to 1/16? Does that still work if I replace the W?
Okay, first, of course, there's the issue of computability. Of course, we want a quantity that is as simple as possible. So this one is already considered too complicated. If you replace that by, 100 of these, might be still true, but we want a quantity that is as easy to compute as possible.
Get a better power of non-circuitry books.
All right. Okay, so why is this very hard to compute? Because there's still four things, xy, xy. What we are going to do is just one, actually two, covariance of x. So we're going to use this quantity to compute, to measure non-commutativity, actually. So if you have a Gaussian vector, if you have a d by d random matrix X, you can treat that random matrix as a Gaussian vector. If you have a random matrix, you can treat a matrix as a vector. Okay, and then you can look at the covariance matrix, and that's a d squared by d squared covariance matrix, and then you just take the spectral norm. Okay, sounds not possible, right? Because when you treat a matrix as a vector, you are destroying the matrix structure. If you destroy the matrix structure, how do you measure non-commutativity? Well, it could, if we compare that to this thing. That's the reason. So here's the reasoning. First, you can always write a Gaussian matrix X as something like this. If all the entries are jointly Gaussian, you can write X as a linear combination like this. And AK are deterministic, GK are IID standard Gaussian. In the case of commutativity, if everything commutes, okay, then they can be simultaneously diagonalized. By simultaneously diagonalized, I mean with respect to a single orthonormal basis, all of them become a diagonal matrix. If all the AK are diagonal with respect to a certain orthonormal basis, that X can be written this way as a diagonal matrix. Okay. All right. So what can we say about the V of X? What's the covariance? Now, if you look at this matrix, treat this matrix as a vector. Most of the entries are 0, so obviously there will be a bunch of zeros in the covariance. Never mind these zeros. Just look at this diagonal. Let's look at the covariance. What's the covariance matrix going to look like? Well, you will see x11. I mean, the covariance matrix of this is really just the covariance of the diagonal. So if you look at the covariance matrix, you will see that it's x11, x22, here, x22 square, expectation, dot, dot, dot. There's expectation of xed square. Okay, and then, okay, never mind the other entries. Most important thing is that the norm of the covariance matrix is at least the absolute value, well, not absolute, they're all non-negative anyway, the largest diagonal entry of the covariance matrix. If you look at the covariance matrix of X, that's what it is, plus a bunch of zeros, okay, a bunch of zeros. That's what the covariance matrix is. So the norm of the covariance matrix is at least the largest one of this diagonal. So it's at least the max of the square root of these, well, they have 0 expectation, so just the variance. Okay. The standard deviation of xii. Okay, on the other hand, if x is equal to this, what is ex squared? Ex squared is just the square of all these, and then you take expectation, and that's exactly equal to this one. Okay. So if they commute, everything commute, then Vx is at least this one. Yes. What?
Should wrap up in 2 minutes.
2 minutes. Okay. And then, so if they commute, then this is true. That means by contrapositive, if Vx is much less than this, then they are very non-commuting. Okay. If they're very non-commuting, as Trop suggests, then we can remove the square log B factor. And that's indeed the case. We can remove the square log B factor completely. Okay, Trop only remove partially, reduce the square log B to log B power 1/4. We can remove that completely. But with another quantity that measures non-commutativity, which is this one. But this one is much easier to compute because for Trop's quantity is xy, xy. Xy, xy is 4 things. Covariance is just, just x and x, just 2 things, much easier to compute this one. But this is only in the Gaussian case. And then in the general case, we also have a sharp version. Yeah, this is the last slide of this talk. And I should also mention that this is John's work with Alfonso Bandera and Ramon Vanandel. Yeah, that's it.
You had it on the previous slide. Can you remind us what's the for if they commute? What's the covariance of X there? What does that evaluate to? In the commutative case? The second term in the commutative case, what would
Oh.
that be?
For the commutative case,
Sorry, in the non-commutative case, I'm sorry. In the,
non-commutative case, this will be much smaller than
but
this.
how?
Well, here's the reasoning. If it
Okay,
is much smaller than the first term, then they are very non-commutative.
okay,
So for example, if you have a matrix where all the D square entries are IID Gaussian, the first one is root D, the second one is just 1, because if all the entries are IID Gaussian, treat that as a random vector, that means a vector with IID Gaussian entries, then what's the covariance? It's just identity. So this is 1, and then that will be root D.
I see, thank you. The questions?
Can you relate the sigma x with wx somewhere?
Oh, wait. This one is the,
No, it's your new the covariance of
Oh.
x.
okay. You also mentioned this, wx is at most the square root of geometric average of these two.
I see. Do you have a lower bound also involve co
No,
x?
no lower bound.
Thank you.
Can you say, thanks. Can you say anything about the sharpness? Because it doesn't look sharp in the commutative case, right?
Yeah, it doesn't look sharp in the commutative case. I think a correct bound should be square root log D, but that's what I can only get log D to about 3/2.
So you don't know, it's like, you can't find an example where it's like, this is the dependence on this quantity.
Oh, wait. Dependence on this quantity.
On the covariance.
No, I think this 3/2 is not the right factor. It should be square log D.
So you believe this is the correct way to measure non-commutativity?
The correctness, okay, I mean, it's a computable way to measure
That's good.
non-commutativity. I should also mention
This is
one
a short,
result. Should also mention one result is the eraser.
Yes, above the text.
Never mind. Okay, if we try to prove something like this, dx squared plus log d to the power beta, and then let's say you want something like sigma star x. Well, obviously a good way to measure non-commutativity, of course, we would want this to be equal to this, right? Because especially for the norm, I mean, if you tensor up the x, it should be the same. It's also good, you know, if it also satisfies some kind of triangle inequality, right? But then it will also be good if in the Gaussian case, GUE less than equal to this, depending on what's the scaling of GUE, whatever it is, square. Most condition I forgot. We actually proved that such an inequality, that would be good, right? It's impossible. It's impossible. So that there's actually no quantity that can measure non-commutativity and satisfy something like this. We proved that it's impossible.
So what's impossible? The inequality is impossible to satisfy this property.
Yeah, so whenever you have such a quantity, sigma star satisfying these properties, we can always construct a random matrix that will break this one.
For some beta or for any beta?
Yeah, any beta.
Wow.
As I think it's one more condition. I forgot which. It's this one more. I forgot what's that. There are four conditions, 4 reasonable conditions. Yeah, for any beta. Yes.
Thanks.
One last question.
So your 3/2 really comes because you use Young's inequality to overcome W2.
Yeah, originally we got 3/4. Even 3/4 is not sharp, and then we use Young's inequality.
But is that really because in the you're doing the integration by parts to get an extra P, or is it because of the older?
I think it's in one of the step. I think in the one of the step I used the Gaussian covariance identity, and then that one will make the log factor not sharp. That's one thing. The other one is that here we gain a geometric average because we use Trop's parameter in the proof, and then here we gain a geometric average. Once we have geometric average and apply Young's inequality, there's also something that contributes to the non-sharpness of the log factor.
Okay, let's thanks Marsh again. And that's it for talks for today, but there's a reception outside.